gravitational waveform modeling that we've been working on with Ricardo and Walter for a couple of years, although the project is currently kind of idle. So if people are interested in getting involved, I think we could use some fresh injection of blood to get this going again. Let me start by sort of explaining why we want to do things like this, like what is the problem that we're trying to address. So as we heard from Satya yesterday, there are many ways, there are many ways to model the gravitational waveforms, but they all have their own approximation schemes involved, either a Taylor expansion in V over C, or in the mass ratio, in the case of the extreme mass ratio, and so on. And then how you treat the merger and the ring down part depends on your own particular scheme. So if you pick a particular waveform approximation that you want to use, you can go ahead and use it to do your detection and your parameter estimation, but you don't know whether that waveform is actually a faithful representation of general relativity at all points. And what people have been doing up till now is looking at numerical relativity simulations, which are pretty much as good as you can get in solving Einstein's equations to try and make good waveforms. But they're horrifically expensive to run. So what people have been doing is building up grids of these numerical relativity simulations. This is a three-dimensional space of mass and the two primary spin components on the two black holes with a mass ratio of 3. And each of these dots is somewhere where a numerical relativity simulation was performed. So it's a three-dimensional plot. It's not very clear, but the message here is that there's only a sparse sampling of this continuous parameter space that's been explored by numerical relativity. And the color of the dots here, this is done from a QMAR paper last year, is taking IMR phenom C. This is not our most up-to-date phenomenological model, but the second most up-to-date one, and comparing how it looks to the numerical relativity simulation. And without getting into the numerical details, green is where they tend to agree well, and red is where they tend to not agree so well. So you can see that given these simulations that we have, there are regions that perform better than others, and in particular, although I can't quite see it on this plot, I would expect the region with a low spin to do better than the ones with a high spin, because the waveforms tend to be simpler. So we want these waveform families to basically be good enough to use for parameter estimation across all of the parameter space that we're likely to encounter when we do our analysis for real signals. And so far, with these near equal mass binary black holes, this hasn't been too challenging, I think. Our numerical relativity has already covered that area. But there's definitely places where we know that the waveforms are not so good. And that can be a problem. Another thing to concern yourself with is that so far these approximates have tended to be based on a limited set of the parameter space. So the mass ratio and the spins being the easiest one. But actually, you have two three-dimensional vectors of spin. And if they're not aligned, then that induces different couplings between the bodies, and that affects the orbital dynamics, and the waveform gets more complicated. So actually, it's quite a large parameter space that you want to explore. Yeah, that's right. Because this M is the total mass, and that just scales out of the NR. Here, I think it should be worst, because that's you've got two aligned spins, and that tends to make the waveform longer. Ricardo, you know more about this than I do, so please correct me if I'm wrong. It's between NR and phenom C. Yeah. I know. Well, it's from the paper that introduces phenom D. So I didn't pick the plot for phenom D because it's almost all green. Yeah, yeah. That's it's just these two. Yeah. Yeah, it looks like they're here actually. So -1 and -1-ish. Yeah. 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 Oh, okay. I didn't make that clear. Okay, so basically the problem is we've got this reasonably high dimensional space of waveforms. It's very expensive to sample it using numerical relativity, but we want to build a family of waveforms that interpolate between the known points in that space. So people have been doing this so far with phenomenological waveforms that are written in terms of an effective series, like we saw on the first day, or with the effective one body. It's done with a slightly different technique. But basically, they include some analytical part and some part that is based on a fit to this numerical relativity data. But there is a problem with that, because you don't know how well you're doing, really. And if you have this mismatch in your waveforms, then that can actually feed through to a mismatch in the inferences that you make using those waveforms. So again, I've taken phenom C and phenom D. This is still from the QMAR paper. I should have noted that. And what people do is they basically do more numerical relativity simulations and then adjust their fit to accommodate them to get a better and better match. And this process could, in principle, go on forever, but after some point, we should be able to do well enough. So better waveform models definitely help. That's why we go from these IMR phenom to IMR phenom B to phenom C to phenom D, and we also have now 4 different versions of the effective one-body waveform, at least 4, because I think there's different spin prescriptions as well. And of course, that makes things better, because if you go from C to D, you see the bias here in the y-axis. Previously was quite bad, and is now much better. There's still a bit of scatter. So that's all well and good. If you're a waveform expert, this is your bread and butter. This is what you are doing in your research program. But there's another way that we can sort of mitigate this problem. The basic problem is that we don't know the error that we have. Because until we've put the waveform there, until we've done the simulation there, we don't know how far away our family is from what we predict it to be. So there's an additional uncertainty. There's a systematic uncertainty in the sense that it isn't caused by the statistics of the data, the noise in the detector. It's caused by an uncertainty about how good our models are. Looking at it another way, if we have a kind of family of waveforms, this is a simplified version. You can imagine the waveform as a function of frequency is a point in a vector space of all this data. So if you have like 1,000 data points, each of those 1,000 points you can think of as being an axis, and you've got a 1,000-dimensional space. And one waveform is a single point in that space that tells you the value of the strain at each of the frequency bins, for example. Does that make sense to people? Because that's a little bit of a leap from what you're used to. So we're going from a waveform that might look like that. So normally you think of this as frequency as the dimension, and the waveform as a function in that space. But you can also think of, say that's 50 hertz. This is a very simplified, 150 hertz, 200 hertz, 250. Okay, I can't draw all thousands and thousands of frequency bins that I want. I can think of this as the dimension. So then I have this vector space that's got one dimension for each of my samples, and then the position in that vector space corresponds to one of these functions, this waveform. It doesn't matter, same number of dimensions, because it's you know, unitary transformation. Yeah, some of the dimensions are useless. Anyway, so a particular waveform is a point in that space, and then if I vary the masses of the waveform, like the masses that I put in and produce the model, then there's two masses, and if I vary two parameters, then it sort of sweeps out this two-dimensional surface in a very high-dimensional space. Okay? So we call this the signal manifold, because if you're thinking of relativity, then you may be more familiar with differential geometry and things like that. And you can frame this whole problem in that language. And it's a shame Sathi isn't here, because he was one of the people that pointed this out. And we were talking about it over lunch yesterday. So I think it's a very beautiful formulation of the problem. So your model lives on this low-dimensional parameter space. But the actual true waveform, unless your model is perfect, in which case it will be somewhere on that manifold, the true waveform in general will lie away from that. And so the bias that you get is basically caused by the projection. When you do your parameter estimation, what you're looking for is the area in your signal manifold that's closest to the observed data. So if this is the signal manifold, I'm trying to reproduce my own diagram. I take the kind of closest point on the manifold to the actual observed sample, and then the kind of uncertainty that's caused by the noise creates a spherical distribution in the vector space, in the big vector space. And what you do when you do parameter estimation is that your uncertainty contours are just the slice through that spherical ball onto this manifold. And if the manifold is curved, then these things don't have to be circular anymore. So if there's a strong curvature here, I don't know, if I draw a very nasty manifold, then my circular blobs are going to give me ellipsoidal style confidence intervals and so on. Okay? But the center of the confidence interval, you can see that the most likely point is going to be the closest one to the true position of the data. So if there's no bias, all that is saying is that your manifold is basically flat and perpendicular to the the error in the waveform. And so if I pick a particular pair of masses, say the true masses were 1.4 and 1.4. If I pick 1.4 and 1.4 in my space and generate the waveform, then the delta vector is perpendicular to the vectors that span the manifold in the local region around the best fit. Okay? So it's unbiased because there's no projection of the error in the direction that I can accommodate using parameter estimation. However, there's no reason for that to be true unless you're very lucky. So I may have actually observed data here, and the closest point may be there, but the actual true parameters may be there. In that case, you have a shift in the parameter estimates that causes this bias that you don't want. So basically, there's an uncertainty in that around this sort of two-dimensional manifold, there actually should be a kind of fuzziness that tells me how wrong my waveform is. And that fuzziness is what I'm going to describe with the Gaussian process, or attempt to describe. Everybody looks distinctly nonplussed. That's how I think about this problem. Let's go back to something a bit simpler. So I want to tell you about Gaussian processes as well. So I've explained the problem that I'm trying to address in this case. Who knows what a Gaussian process is? Raise your hand. Okay, we've got a few. For those who don't, I'm going to try and explain it. Hopefully everybody knows what a Gaussian distribution is. This is the famous bell curve probability distribution. It looks like that. And what it is expresses a probability of a variable, sometimes called a random variable x, taking a particular value in the real axis in one-dimensional space. And it's parameterized. You need two numbers to fix your Gaussian distribution. You need to know the mean, which could be 0, and you need to know standard deviation. This is like the absolute basics of statistics. So hopefully everybody has heard of standard deviations and so on. If you're doing experiments, this is absolutely vital knowledge. So these two parameters, mu and sigma, okay, the standard deviation squared with variance, sigma squared, I'll probably use the two interchangeably, but basically what I'm talking about is the width. So for one dimension, it's given by this equation, and then you can generalize that to a higher dimensional space by converting your mean is no longer a number, but it's a vector, it's a position vector space. So it could be like here, for example. And instead of having a standard deviation or a variance, sigma or sigma squared, you have to know not only the width in each of the directions in the vector space. So if I give you, say, a two-dimensional Gaussian distribution, in a simple case, it would look like that. And that can be written with the product of two one-dimensional Gaussians, but you want to be a bit more general than that. You want to allow it to take shapes that have some correlation between the parameters. So with two numbers, you can have the two one-dimensional Gaussians and multiply them together. But in order to get the full general shape, the correlations, then you need a correlation matrix. So that's capital sigma in this equation. Yeah, it's a diagonalizable matrix indeed. Well, diagonalizing the covariance matrix corresponds to rotating my axis, so choosing these coordinates instead. And in order to convert from this coordinate system to that coordinate system is a rotation matrix, so I can't really escape the fact I need to know the matrix elements. So, okay, you can factorize it if you choose the right basis, which is useful, but then to get back to the thing I'm interested in, you still need to know the diagonal element, the optimum. Yeah, exactly. You can't, you can hide it under the carpet, but you can't get rid of it entirely. Okay, this is standard. So Gaussian process, if you think about then, say instead of a two-dimensional vector space for my points, I can go up to three-dimensional, four-dimensional, 1,000-dimensional in the case of the waveform manifold that I was talking about. The Gaussian process is the infinite dimensional limit of this. So it's like going from quantum mechanics to quantum field theory. And things that were previously vectors become points in a Hilbert space, and things that were previously correlation matrices become operators, basically. If you're used to doing that kind of physics, then this may be a useful crutch to try and think about this problem. But statisticians don't know any of that stuff, so they have different words for these things. So when you go up to infinite dimensions, then instead of having a point to represent each dimension, you can think of this as there's a dimension for every point on the real line. So there's an infinity of dimensions given by this continuum. And I get back these nice functions that I want instead of these slightly weird points for each of the samples. So this Gaussian process is the equivalent to a Gaussian distribution, but it's defined over the space of functions instead of over the vector space of samples of data or whatever I have. Does that make sense? So instead of having a mean vector and a covariance matrix, I have two functions, a mean function and a covariance function. And they are totally analogous. That the mean is just the expectation of the function of the, x is your variable that gives you the sort of continuum. And the covariance function, again, is telling you what you expect the correlation to be between the function as you make as you move between points. So if this is like a kernel, in the, if you're doing a Green's function or something like that. So a sample from a Gaussian process, if you see it in the literature, you just write this tilde. This is how statisticians say that this function of x, is a sample from a Gaussian process that has a certain mean function and a certain covariance function. Yeah. So this is basically capturing the correlation structure of your functions. Mm-hmm. Yeah, but I think it's not two Gaussian variables here. This is it's like saying what's the correlation between what's the shape of the distribution in two-dimensional space. So like this thing here, yeah, x is like x is the argument of the function. The function is the thing that's random in the Gaussian process. So it's like one level up from a Gaussian. So I'm not picking a random x, I'm picking a random function of x. That doesn't answer the question. Yeah. Mm-hmm. I could draw a picture, actually. I think that might make it clearer. So say I have a function that looks like this, and let's go back and discretize that function. And each of these now becomes a point, each of these is now a dimension in a three-dimensional parameter space. Let me just do 2 because it's simpler, and I can draw it. So because this function is smooth, you would expect that, nearby points are highly correlated because the function I've drawn is a nice smooth function. So that's like saying, okay, if that's x1 and that's x2, then the expectation of x1 minus mu1, x2 minus mu2, that's the diagonal element in the covariance matrix, right? It's saying if this is high, if it's 1, then it means that neighboring points are highly correlated with each other. And if it's 0, then it means that they're not correlated with each other. And if in fact, in the case that this kernel function, if it's a delta function, in that case, there's no correlation between adjacent points, and that is just Gaussian noise. Okay, so that's like the simplest case, so there's no structure there. Does that make sense? Does that help explain it? Like, it's kind of like a metric. It tells you how far you have to go before you are uncorrelated. Did I? Yes, that's right. Okay. Yeah, so if there's no correlation, or if the correlation timescale is very short, then I draw a sample from that Gaussian process. It will look like, noise. And if it's large, then the timescale is long, and it'll look like smoothing. So you can sort of zoom in and out as well. So it's kind of setting the scale of the wiggliness of your functions. Yeah. Or it could be frequency, if I want to try and interpolate, a waveform in the frequency domain or something. It could be anything, really. Yeah. Well, I'm not going to really get into that because I don't know the answer. But that's for the discussion. Okay, so this is a sample from a Gaussian process where the mean is 0 and the variance is 2. Oh, sorry, this variance function is just a constant, it's 2. So you can pick random functions from this distribution, and they may look like these things. Each of those lines is a sample from the Gaussian process. And the gray envelope is kind of the uncertainty on those functions if you think they all live inside that envelope to one standard deviation worth. Okay, I'm going to flip. Well, okay, I've got 2 more slides. I just want to say one thing. What is all this about? It's very abstract. What on earth are we going to do with this? Well, okay, this is just setting up the problem, because what you want to do is you start with your Gaussian process that has some prior on the mean vector and the covariance function. Sorry, the mean function and the covariance function. It has a mean of 0. Yes. They all have to be smooth because it's kind of infinitely differentiable, but you can differentiate it infinitely, you know, unless the kernel is like a delta function. So that's kind of the opposite case, I guess. A constant is a, you know, straight line delta function. So if it's a constant, then they will be smoother than if it's, you know, yeah. But then the scale of the oscillations is also random. So I think it's a bit abstract, so I can't really explain it intuitively. But when we start to learn about the kernel function and the mean function, then you can see a bit more of the effect it has. I'm going to flip over. But before I flip over to the demo, the general idea here is that we start with this totally uninformed Gaussian process, and we feed it some information that it learns. So it's sometimes called a machine learning method. It's quite different from the neural network, but in a sense, it's like it can be used to interpolate things in a very agnostic way, and it doesn't matter what the you know, you don't need regularly sampled data or anything like that. You can just feed it any information. Say you know the value of the function. Okay, let me actually go into specifics here. So the Gaussian process itself means that if I take some values of the x-axis, x, and then take a sample from the Gaussian process, then I'll get a function f of x, which is f here. Now, if I say I've evaluated my function, say I have an unknown function, I want to approximate it with the Gaussian process, then I evaluate that function, it could be the waveform, at different values of x. I get f of x that I know, because I've actually done the work to find out what the value is there. Then I can feed that information, those known points, into the Gaussian process. And it will learn, given that information, it will update its mean vector, its mean function, and its covariance function. Okay? This is just using Bayes' theorem to learn. So I start with the prior, that's the totally uninformed Gaussian process. I give it some data, that's the function sampled at known values. And what I get back is a posterior distribution, a posterior Gaussian process. So I can write then the posterior predictive distribution conditioned on this input data. Yeah. That's the kind of slightly annoying thing about the Gaussian process, is that you need to know what the kernel is. You can choose all kinds of different kernels, and it doesn't, you know, you can, if you have a family of kernels, then you can pick the best one in the family, but it's up to you to decide what a reasonable family is. Why was I erasing this? I can't remember now. I was going to write Bayes' theorem, but I think everybody knows what that is. Okay, so then after I've learned about this, I can, okay, starting off, how do I do this? I have the joint distribution. This is just for a non-Gaussian process just for random variables so you can see the analogy. Let's say I have x and y, right? Then I can write p of y given x times p of x, right? This is not even base theorem, just factorizing the thing. So this is the predictive distribution on y conditioned on a certain knowledge of x. So this thing here is what we get when we feed this model some specific values of x. And likewise, if we feed it known values of f and a kernel function, then we can predict what the values of f star, the stars denoting unknown points, given the things that we do know. So in this case, I can write a draw f star, that's the value of the function, at an x star that I choose, that's the places where I want to do the interpolation, and the x's and f's that I already knew. And the nice thing is, okay, I went around the houses to get here. The nice thing is that you can write down that as a Gaussian distribution, or as another Gaussian process, which has a mean vector given by the projection of the known points onto the kernel function like this, and an updated covariance function that's given by this. This is just done by a bunch of algebra. If you like work out how to reduce the dimensionality of this matrix and this vector, this is what drops out. Yeah. Yeah, I mean, again, going back to the two-dimensional case, it's like if I have a two-dimensional Gaussian and I know the value of x, that's equivalent to taking a slice like that. That's what I'm doing here. I'm taking some known value, and then the projection of that distribution onto y, p of y given x, is how this thing looks in the slice. So it's like going to be like that. Okay? So if you write down the matrix for this, then you know, the mean is given by this bit, and the width is given by that bit. So there's a bunch of matrix identities that you can use to do that. But you can see from the picture how it works, I think. And when you do that, then you can see the Gaussian process has, as if by magic, updated its envelope to have no width at the points, because you want it to give you an exact prediction at the known points. And instead of having this completely agnostic range of functions, you can see that now the envelope tries to interpolate smoothly between the known points. Yes. I'm not going to talk about that, though. Yeah. Yeah, so just to say, I mean, the kernel can have a component that gives you a residual uncertainty even when you have an exact value. Okay. How is everyone doing? Is this boring or is it just confusing? Let's liven it up a bit. So I've got an IPython notebook here that I'm going to use to show you how this works in practice. So this is what I was saying before. We've got the Gaussian process. It's completely defined by the mean function and the covariance function. In this case, well, the kernel k. Now let's talk a little bit about the kernels. So a nice one to use is the squared exponential is a pretty common choice. And it's nice because, of course, this is just another Gaussian. So, you know, Gaussians upon Gaussians is Gaussians all the way down. and then you can parameterize it. You can add a couple more variables, give it a sort of scale, an amplitude sigma, and a scale that's like a correlation length scale tau, for example. And then you can learn what these parameters are. Once you've fed it some training data, you can adjust tau and sigma to give you the best evidence for that training data under this family of kernel functions. No, because I broke the code. Okay, so that's the kernel I just said. I've written it in the Python notebook. I just want to show you what it actually looks like. So if I plot that kernel, you see it's diagonal, x and x prime being the two directions here, and the closer they are, of course, the higher the value of the kernel. So it's saying that the sort of length scale for this kernel function and therefore this Gaussian process is kind of this width. Such a stickler. Oh no, it's the same. Yeah, it's the way Python plots matrices. I think it inherited this from MATLAB. This is the origin, right? And that's, yeah. Okay. I could choose a different kernel if you like. You can use any function here. So we can have a play around and see how it works. So this particular kernel is useful when you expect nearby points to be correlated but not to have correlation on longer scales. So that might be a good one for like a noise process. In fact, all the noise processes that we use for our Gaussian likelihood or the Gaussian noise in LIGO are actually examples of Gaussian processes. But you're probably not used to thinking about them like that. The kernel in that case, in the case of LIGO noise, is given by the, okay, so they look at one of the dimensions here. If I went down from 0 to 100 in just one of the axes but kept 0, then I would be looking at the kernel for LIGO noise. What I would get is the Fourier transform of the power spectrum, because the power spectrum is the Fourier transform of the zero lag autocorrelation function, which is what this is. So people find, I always read about that when I was a grad student and thought, oh, that's weird. But only through sort of playing around with these things a bit has it actually made a bit more sense to me. So we can try checks. But, I mean, it's up to the user to decide what they want for this kernel function. So if I had something like a sinusoid, let's say it was, it was oscillatory and there was a couple of components in it, a couple of frequencies maybe, then I could choose a kernel function that was, A1 sine omega 1 x minus x prime plus A2 sine omega 2 x minus x prime. Okay? And that would give me a kernel that had correlations on two different length scales given by omega 1 and omega 2. Does that make sense? So it would say that after I wait omega 1 time, then I would see a correlation again. That might be like this time scale. And also, if I wait omega 2 time, then I would see a correlation again. That might be like that time scale. I didn't draw it. I can't just draw samples from Gaussian processes. Well, I can because it's an infinity of functions, but that's not the right one. And you can imagine then if you have like each of these omegas could be the bins in a Fourier transform, and then each of the A's is the power in that bin. So if I take the kernel function corresponding to the Fourier series, you know, or the inverse Fourier series, A1, omega 1, A2, omega 2, A3, omega 3, that would give me a Gaussian process with a kernel that's given by a particular power spectrum. So it would tell me how the correlation of the noise looks in the time domain. So all these things are kind of interlinked. We can try that with the code if you like, but I want to show you how it learns now. So let's simple example. This is the equations that I showed you in the presentation to update my predictive distribution given some known f and x to give me the unknown f star and x star. Okay, so I've coded it up here. I can send this notebook around later if anyone wants to play around with it. It's fun if you like that kind of thing. So let's start off. I give it just a single point here. This is my input data. I'm going to fit a very simple function, just a straight line with a gradient m to the Gaussian process. So I pick my x like this, and I have y equals mx. Can't get much easier than that. Then what I will have is the predicted distribution is the prior distribution conditioned on this particular value of y and this particular value of x. This code is a little bit messy, but you get the idea. Then what I'm going to do is pick x star is going to be, you know, an axis between -10 and 10 with a, you know, sampling period of 0.1, and I'm going to predict my value of the function at these new x stars, the unknown points that I want to interpolate. Okay, and if I do that, you'll see that what was previously just a uniform band has tightened up so that it has no width at that point that I fed it. Where x is 0 and y is 0, it lies exactly on the line. So this blue line is the mean function, and the envelope is the covariance function, the width of the covariance function. Now, the covariance function is a function of 2 parameters, so it can't be, this is what it is projected onto just a single parameter. So there's actually correlations in here that are being smeared out by the way I'm plotting it. So it's a little bit more complicated than the graph can show. Just to show you how this works, then say I feed it another point at 0.1, then it's learned that in this region there's a lot less uncertainty between these 2 known points than there is outside the range of the data. So you can see that away from the known points, you're still getting the prior. It's this nice uniform broad thing. But then when you start knowing the data, then it says, oh, there's a line in there, and it must be quite close to that line is where I expect the function to live. No, now the prediction is the rest of the, the rest of the real line. And the red crosses are the data that I fed it. So knowing that these things are exactly here, where is the rest of the function? So I've picked a length scale of 2 and an amplitude of 1. So if you're right, let me do, say, you want to do, what do you want your length scale to be? And what do you expect to happen here? Let's see if you're right. You are. So now you see that it knows that the function must be fairly smooth on a scale of 0.1. So within like 0.1 of the known points, the error collapses dramatically. But then in between, it still gives you a big error like that. Yeah. Then if I was to feed it more information on a finer grid, of course, then it would learn again with that particular time scale, length scale, that there is a little straight line in there with no error. Okay? Yeah. So you have to basically write down. You can write down the evidence for your training data for a particular choice of sigma and tau, and then maximize that evidence and pick sigma and tau that way. Or you can, include sigma and tau as variables in your overall problem. Yeah. And then you can integrate over them as well if you like, given the training data. But it's quite computationally expensive because the problem with this matrix formula, as you will probably notice, let me just go back to the PowerPoint. So this thing here involves a term that is the correlation between all of the known points and all of the unknown points. So if you have a lot of data that you know, this matrix becomes very large, and it actually goes like n cubed is the computational cost of this method. So it's a bit expensive. No, this it just does that. Okay. So I was going to say at the end that you can download a few professional packages. There's two that are good. One called George is written by the guy that wrote MC. That seems to work quite well for small problems, but it tends to break when you give it a lot of data. And then there's scikit-learn as another Python package, which has a bunch of nice, well, not just Gaussian processes, but lots of other machine learning methods. And I think they're written in C underneath, so they tend to be a lot faster. So scikit-learn, I think, is suitable for fairly large problems, but I haven't tried it as much. The one I've got in my notebook is really just written from the ground up as a tutorial, so we can sort of fiddle around with the innards a bit more. Okay, so has everyone got some kind of intuition for what these things do now? If somebody said, I'm going to use a Gaussian process to interpolate a bunch of climate data, you would go, oh yeah, that makes sense. What timescale are you using? What kernel are you using? Is it seasonal? How does that work? Okay, good. So you've learned something. Some of you have learned something at least. Exactly. A cyclostationary process must be something like this. This is a sort of generalization of a lot of these techniques. So I think there must be a way that we could do it using that. I want to just do one more experiment before we go back and wrap up. Yeah, I've not talked about gravitational waves for about 20 minutes now, so we should connect back to reality at some point. Yeah, I want to try a different kernel. Does anyone want to suggest a function? It can be anything. Let me just add a sinusoid. That seems simple. With a time scale of tau again. Yeah, that's a good one. Let's do that. Let's do a sync function. Okay. So the sync function, there probably is a Python version of it, but this one may have a pathology at t equals 0. Yes, unfortunately it does. Is there a numpy.sync? I don't think there is, sadly. So this is the advantage of live coding. There we go, that's better. Okay, so what's going to happen here is that I expect there'll be some oscillatory part in our model. So we start again with the just one data point, I guess, to see what happens. And it crashes. How do you check for a 0 vector in NumPy? Yeah. I'm not sure that's right. But it should stop from crashing. Okay, so we've still got the nice tight bound, but there is some oscillatory part. Just do a couple more points. Oh, it doesn't like my sync function very much. That's a shame. If that doesn't work, I'm going to give up. We can play around with it offline. Yeah, it's because my code is a mess, basically. I'm sure you can find singular matrix even. That's nice. Yeah, so as you can see, the choice of the kernel function is very important. Okay, so let's go back now. I actually wanted to show you this applied to a waveform. So I've generated a couple of waveforms with different PN series, but for some reason, again, probably for a related reason, it was crashing when I tried to do it. So I need to rework this. We did have it working with Ricardo a while ago, but I'll show you the output from that in a minute. Mm-hmm. Okay. Yeah, the problem is on my old laptop, it was all fine, but I foolishly changed laptops when I moved to Glasgow and lost all my stuff, or didn't copy it over at least. Okay, so you got the general idea. You understand now a little bit about what the Gaussian process is. And you can probably see that this is a useful thing to apply to a waveform when you don't really know exactly. Say you have the training data as the numerical relativity, and you want to know what my errors look like when I go away from the numerical relativity data. The Gaussian process is a good way of doing that, because you can train it on your input data, and it will learn the kind of structure of the uncertainty and so on. That's the idea, yeah. Yeah. So you take all, you might have a grid of known NR waveforms, and you want to know in between, I want to know, given all this stuff that I do know, what's the waveform like here? Yeah. Yeah. Are you talking about the noise in this case rather than a signal? Ah, okay. Yeah. Yeah. But are you talking about the waveform or the noise? The waveform. Yeah. Well, one thing you could do is it's like waveform reconstruction in a sense. If I know, say I've been taking Lisa data for 6 months and I've gone, wow, look, there's a black hole binary, but I don't really know what the masses are. Okay, that's a bad example. Say there's some gravitational wave that is completely novel, and I don't know what it is. Then I could use the Gaussian process, train it on the data that I've seen, and I could include the uncertainty due to the noise instead of just having these perfect accuracy points, and use that to predict how I would think that it would evolve in the future, for example. Okay. Yeah. It's a really nice, there's loads of different applications for these things, but I like it in particular because it kind of unifies understanding of power spectra, sync interpolation. All these are just special cases of a Gaussian process. So a lot of the tricks of the trade can be written in terms of this sort of language and kernels and so on. Okay, let me just wrap up and tell you a little bit about how this has been applied in the literature so far. Christopher Moore, who's at Cambridge with John Gare, and now is still in Cambridge, but with Uli Spirhaka, has been working on this a little bit, and they've taken an approach. They're trying to see whether this works for H of T, which is similar to what we were doing with Ricardo, but we don't have a publication ready. So I'm going to first tell you about their work, because they're more advanced than we are, but they're using a slightly different application. So here they've just looking at 3pn and 3.5pn as an example, because you can easily generate 3.5pn waveforms. It's not so easy to generate numerical relativity waveforms. And what they do is they just write down H of T and take the difference between the 3pn and 3.5pn waveform and use that as the uncertainty that they're trying to fit with the Gaussian process. So then you go through the machinery that we've talked about, you condition your process on the known data and try and predict the uncertainty in the unknown data. So lambda here is like the mass ratio, for example. Now the nice thing about doing it this way is then you can write down the likelihood for the gravitational wave data. I'll talk more about that tomorrow. I don't want to get into the maths there. But those of you who know will recognize that this is the Gaussian likelihood for the gravitational wave data analysis, where your H of T has been replaced by capital H, which is like the 3pn, plus delta H, which is the unknown difference between the 3pn and the 3.5pn waveform. And because it's additive in this way, it means that you can split it out of this linear inner product thing and analytically marginalize over the unknown parameters for the Gaussian process. So the uncertainty from the Gaussian process actually drops out. Well, it doesn't drop out, but you can integrate it out. And then you get a nice closed form expression for the resulting likelihood function that includes the Gaussian process error, like so. So basically, all it does is it modifies your covariance matrix for the noise with an additional unknown component due to the waveform modeling error. So just to show you, this is a difference between 3 pn and 3.5 pn at a given chirp mass, and that's the time. And you can see that it's highly oscillatory because there's actually, you know, a dephasing of the waveforms, and when you convert that dephasing into, you know, e to the I delta phi, then that tends to cause lots of wiggles, and it gets worse at higher frequencies because the two waveforms diverge faster at high frequency than they do at low frequency. And likewise, once they've done that, they can estimate the uncertainty from in the waveform from the Gaussian process, and you can see that if you scan across chirp mass, they've trained it here where it's pinned that down to 0, and then in between it's saying, okay, there's a bit of uncertainty from the waveform modeling error. And outside the domain of the training, that error starts to blow up. So again, it's sort of telling you that when I start doing extrapolation instead of interpolation, that I am in dangerous waters. So I should have a big error. And then they actually did the full thing and went through to a one-dimensional parameter estimation problem. This is what they get when you try and fit the 3pn waveform to a 3.5pn data. This is the true value of the chirp mass is 2. And if you try and fit the 3pn, you get 2.06 instead. And so you would expect, and indeed is the case, that once you include the Gaussian process uncertainty, that kind of magically corrects that bias. In the black here is what you get if you do the 3.5pn analysis. The dashed line is the result of the 3pn plus Gaussian process analysis. So that is with the error, the extra error coming from the Gaussian process. You can see it's having the effect of kind of broadening your estimate of the chirp mass. But that's okay, because there is actually some systematic uncertainty that you've converted into a systematic uncertainty on the parameter estimation, but it's actually unbiased. So it's giving you a nice, correctly saying I'm less certain of the true value, but I know that I'm going to be unbiased. So it seems to work. I mean, it looks like it's a promising technique. There are other ways that you could do it. I'll tell you a little bit about the way that we were doing it. So H of t, you saw these the advantages that you can get the analytic marginalization, so it's no slower than doing a standard parameter estimation problem, which you know is computationally expensive. But the function oscillates quite quickly, and so the errors can be a bit large, because you know your kernel has to vary on many different timescales, and so it's difficult for it to learn that very wiggly function. It depends on your choice of the kernel, for example. If you know something about how that ought to look, then you can use that information and choose a good kernel. So there's kind of a bit of manual tweaking that you can put in. The way that we were trying to do it with Ricardo and Walter was to use the amplitude and phase instead of H of t. So we decompose that into the argument and the modulus, and we have delta A is the ratio of the numerical relativity to the post-Newtonian amplitude, and delta phi is the difference between the numerical relativity and the post-Newtonian phase. And we use these two things as our functions that we want to do interpolation of with the Gaussian process. Actually, yes, we do it in frequency space. I've probably just put the wrong argument in these things, but it's all. Oh no, actually, the plots are in the time domain. I'm pretty sure the code works in the frequency domain, so I don't know how that's happened. I took these from Ricardo's document. So this is just showing you the amplitudes from different waveform families and from numerical relativity. Okay. So you see that not only are they a little bit different down here, they get worse at higher, well, as you get closer to the merger, and numerical relativity actually continues off the end. So you need to deal with that extra data somehow, technical details that we don't want to talk about now. And likewise with the phase. Yeah, I didn't have that one. Likewise with the phase difference, you can see that instead of being this really wiggly function, the delta phi is actually quite smooth and only starts to get divergent at the very end. So this is a much better candidate function for interpolation than the oscillatory h of t on its own. And so I would expect that our prediction of numerical relativity should be better than it would be if we just did the raw h of t. But there's a bit of a problem. Okay, before I get to that. Yeah, so advantages are we can interpolate over the, wait, hang on a minute. Did I change this slide? Yes, so the setup we were using is that we do Gaussian process in multiple dimensions. So we went very excited about Gaussian processes and thought, well, we'll try it for everything. This is an experiment that I'm describing here. This is not the final mature research work. So we did interpolation in the frequency domain, the dimensionless frequency domain, so that we can take the numerical relativity waveforms, factor out the total mass, and use the same interpolation function to predict the waveform for any given mass, which is nice because GR has this cool property. It doesn't depend on the mass. And then we used another one to interpolate each of those waveforms across the mass ratio. So eta being the symmetric mass ratio. So then the question arises, I've got one process that interpolates in frequency and another one that interpolates in eta. And what I actually have is like at each training point in frequency, I have another one that goes across eta. So it's a sort of two-dimensional array of Gaussian processes. This is probably not the right way to do it. I think there must be a more efficient and possibly better way of just doing a joint Gaussian process on two-dimensional parameter space instead of one. Yeah, it's whether you include correlations between frequency and mass ratio, basically. Disadvantage to our method is that, we've got these Gaussians within Gaussians, and they all need to be evaluated. It's kind of slow. Also, we can't analytically marginalize out the uncertainty in the phase, because if you try and do these integrals, you get bogged down in a huge infinite series of Bessel functions, and nobody likes that. So what you would probably do in practice is sample the Gaussian process along with the waveform, the physical parameters of the waveform. So if you do a Monte Carlo, you're jumping around in mass space. You also take a random jump in the Gaussian process space as well. And once you keep doing that over and over again, then you're effectively sampling the right uncertainty distribution as well. But that just adds an additional layer of complication to things. So I think it's a question of whether it's worth doing all that, whether it can be made fast enough to get the benefit of having a better interpolation. And that's kind of one of the things that we need to work out. Yeah, yeah. It's slow compared to the analytic version that Moore has. And it's, well, okay, Moore's version is basically the same speed as normal parameter estimation, which is already quite slow. So making it more slow is in the wrong direction. And people get impatient when we make a detection. There's always an urge to rush and write a paper. So we don't want to wait around for these kind of things. Okay, so just finish up some plots. So I put all this together, interpolation in the mass ratio space. I trained it on a couple of different NR waveforms, and then I compare the Gaussian process prediction to the numerical relativity waveform. These are in the frequency domain, so they look a bit weird. But you can see that actually if you compare the dashed lines with the solid lines, you know, there's still a bit of error here. This is just the mean function that I'm looking at. So especially when you get towards the end of the in-spiral, which is at, you know, 1500 hertz here, then the phasing gets bad. But actually, it does a pretty good job compared to post-Newtonian of just of capturing both the amplitude and the phase. So I would be happy to use a waveform that was only biased by this amount rather than many, many cycles. Yeah, the training set, there's no error on the training set, so it would be identical. Yeah. Unfortunately, I can't reproduce them in the notebook, because that would have been the best thing, is that if we could actually have done it live, which is what I wanted to do. So I'm sorry about that. Zooming in, you can see, you know, at the low frequency end as well, there's a, you know, fraction of a radian difference between the real one and the interpolant, but it's still pretty good, I think. Unfortunately, we didn't run it all the way through to a parameter estimation algorithm, but that's probably one research project for the future. Just to wrap up then, this is all very experimental. I think proof of concept in simplified case was done by Moore. We are trying to take a slightly more sophisticated approach, but it is more complicated to implement it as well. So there's still a lot of work to be done to see whether it really is going to solve the problem, and then apply it to real data to see whether, you know, it actually helps. Then there are other things you can do with these Gaussian processes in the area of waveform modeling. One paper that came out just over a month ago is Zohair Doctors with the Chicago group are using the Gaussian process uncertainty. When that uncertainty is large, it means that the existing numerical relativity simulations don't tell you much about the waveform in that part of the space. So that is a good place to put a new numerical relativity simulation, because there you get the best bang for your buck and learn the most. So they're using these things in a different context, but similarly, it is a really nice way of doing that, because it sort of captures the structure of what you do know. Another thing you could do with them is apply them in the context of reduced order models, where you still have some kind of an spline-based interpolation in frequency, or a sum of basis functions in frequency. So I'm thinking things like SEOB and RV2 ROM, for those in the business will know the jargon, is made of lots of splines in frequency, sampled at reduced set of basis points in frequency. And then it uses splines in mass ratio to interpolate those. So it's actually spline-based version of the stuff that we're doing with Ricardo and Walter. But spline interpolation is lousy in 7 dimensions, because you need basically a uniform sampling of your grid, or at least something approaching uniform anyway. Whereas the structure in the waveform is by no means uniformly dense at all points. So one potential application that I think could work well is to replace the splines in parameter space with Gaussian processes, because then you can start just doing sampling in the places that you really care about to learn what the model looks like there, instead of having to do these splines that are kind of overkill or underkill, depending on where you are. So that's another thing that we could try. The technique itself is really, I like it from a theoretical point of view. I've tried to explain to you roughly what it means, and I think you probably already have in your head that could be useful for such and such a problem. So forgetting all about the waveforms, which is one of our personal problems, there are many other applications to this in astrophysics. So if we're talking about fitting the density profile of the galaxy, this could be a way of doing that. You could also talk about interpolating noise and so on in LISA, or presumably in pulsar timing arrays. You guys are on top of the data analysis. You've probably thought about these as well. I didn't see that one. I apologize. I should have put it on my references. Excellent. Okay. Yeah, so I think it's a nice technique. From a data analyst's point of view, I find it good. So hopefully now you will understand a little bit more about Gaussian processes and how to use them. Okay.